Hi everyone, welcome to week 3, part 2, the lecture for ESS 3, Oceanography. Today we're going to be talking about tides and then we'll get into waves and coastlines. So today we'll start with learning about the tides on Earth. So with that we will be able to explain and also understand and draw diagrams of the two tidal bulges on Earth on both sides of the Earth. Then we'll go into why we have tides, including the daily tides, so high and low daily tides, the cycle of tides that varies monthly, so spring and neap tides, as well as some other complicating factors. We will go over each of those, and then we're going to look at some tidal patterns on a graph, which you will also be able to do in your discussion next week. So on Tuesday, the discussion, you will be looking at some real tidal data, actually from Newport Beach. So first, what causes tides? So tides are due to a combination of the gravitational pull or attraction of both the sun and the moon. So it's not just the moon that causes our tides, it's also the sun. The sun also exerts a gravitational force on the Earth. So if you look at this equation here of gravitational force, you'll see that the force is equal to some constant times the mass of the two objects divided by the distance between them. So for example, the mass of the Earth and the mass of the moon divided by the distance between them. So the size of the objects in question, as well as the distance between them, play a really big role, or really the only roles, in the gravitational attraction between those two objects. So when we look at the Earth tides, we look at the moon and the sun. So the sun is gigantic in comparison to the moon. It's gigantic in comparison to the Earth, and the moon's smaller than the Earth. The sun is huge, but it is significantly further away from the Earth. So on the Earth, our tides are actually most influenced by the moon because the moon is closer. The secondary influence, not quite as strong, is from the sun. So even though the sun is much larger, it is very, very, very far away. So if you look at this figure down at the bottom, this shows the distance to scale between the moon and the Earth, so they're very, very close, compared to how far away the sun actually is. This shows the size to scale. So here we see Earth and the moon, and see how much bigger the sun is. But when you think about how far away it is, that's when you can understand that the moon actually does have the most influence over our tides. But we do see influence from both. So what causes our tides? The tides can be seen as a bulge of water on either side of the Earth. So in this case here we have an arrow that says the moon is in this direction. The water is going to bulge towards the moon, but also away from the moon. So you have these bulges on both sides of the Earth. So the tides are due to this bulge, the fact that we're rotating, the fact that the moon is revolving around us. And then we also have daily high and low tides, a monthly cycle of tides, and then a couple of complicating factors. So I'm going to go through each of these 3 bullets for the first part of this lecture. So the gravitation, the attraction between the sun and the Earth and the moon is responsible for the majority of the tides. So like I said, if the moon is over here, here is a bulge of water being pulled towards the moon from that gravity. Why do we have a bulge on the other side as well? There is always a sort of double-sided bulge. So there's a bulge of water on both sides of the Earth. It's always going to be aligned with the moon. But why do we have the bulge on the opposite side of the Earth? It's because here we have the moon, here we have the Earth. What is closest to the moon is going to feel the strongest gravitational pull. So the ocean water, this is not to scale, it's not this much water. This side of the Earth, for example, is going to be pulled strongest. So this side of the Earth will be pulled the most towards the moon. The center of the Earth will be pulled, not the, yeah, I guess the center, but also the center in terms of the diameter and circumference will be pulled towards the moon a little bit less than the close side. And then the far side of Earth is going to be pulled the least amount towards the moon. So what that ends up doing is you have very little pull here, more pull here, and the most pull here. So the most pull pulls this bulge. Then you actually sort of pull the Earth out of the bulge. So here you have almost no pull. Here you have even more pull. This creates the tidal bulge that's actually on the opposite side of the moon, so in opposition to where the moon is located. But that bulge will always be in alignment, so the two peaks will always be in alignment, and they'll always be aligned directly to the moon. We'll get to that towards the end in the complicating factors. So the first piece of understanding our tides is to think about the high and low tides that we see every day. So high and low tide daily is because the Earth is rotating. So the Earth is rotating, but the tidal bulge is not rotating. So the Earth is rotating much faster than the moon is revolving around the Earth. So the bulge is going to be fixed in position in alignment to the moon. And then if here you are standing and the Earth is rotating, you will, in 6 hours, you will rotate out of the bulge. So now you're standing in low tide. And then 6 hours later, you'll rotate back into the other side of the bulge. So here we are. And then 6 hours later, you'll rotate back into low tide out of the bulge. Another 6 hours, you rotate back to your starting position, which will be in the bulge. Now, the moon orbits around the Earth every 29.5 days. So when you return to your original position after 1 day, you will not be in exactly the same position within the bulge that you started. You have to actually go a little bit further to get back into the peak of that bulge because the cycles are not perfectly lined up. So this is why the time of the high tide changes daily. So we don't have high tide at 12, low tide at 6, high tide at 12, low tide at 6 every single day. It actually shifts because the moon orbiting the Earth is 29.5 days. So the high tide timing will actually get a little bit later each day because it's going to take a little bit longer than 24 hours for you to return back into that high tide spot. So I have some videos. There are two. They're similar from the same location. I could not decide which one to play, so I'm going to play both. This one is a time lapse. Here's low tide, lots of people out exploring. You can watch the water coming back in as the Earth rotates into that tidal bulge. So this is the place on Earth with the most extreme tidal changes. So the tide changes daily about 40 feet, even more than 40 feet sometimes. So here is the same location, but there's some scientists doing a kind of cool and also very fun experiment.
The Bay of Fundy has the highest tides in the world. What better place to experience these massive tides than the Hopewell Rocks? These brave souls set out to demonstrate how quickly these tides rise. Tides are caused by the gravitational pull of the moon and the sun. This pull causes a large wave of water, known as a tide, to work its way around the Atlantic. As this wave enters the Bay of Fundy, its unique shape and length transforms a small tide into a giant. The rate that the tide rises varies throughout the day and throughout the month. At the Hopewell Rocks, it can rise over 1 vertical foot every 5 minutes when at its fastest. This demonstration was filmed on the highest tides of the season. With the tide halfway in, it took only 27 minutes to go from our feet to our chins. That was only 5 of the 46 feet that the tide rose that day. Come witness this wonder for yourself at New Brunswick's Hopewell Rocks.
So it took them 27 minutes for the tide to rise from their feet to their chin. You would not want to fall asleep on that beach. You might get stuck. All of your things would definitely get wet very, very quickly. So that is the strongest tides, so the highest amplitude change, over 40 feet. So in addition to the Earth spinning in and out of that tidal bulge, causing our daily high tides, we also have to think about what else is causing our tidal changes. So this is real tide data here in feet. If we were only accounting for the fact that the Earth was spinning in and out of the tidal bulge, this would be much more even. So we would have the same high tide levels and the same low tide levels every time we are in high and low tide. But you notice that high tide sometimes is higher, sometimes gets lower, sometimes gets higher on about a monthly scale. So we call this spring tide and neap tide. It's the monthly influence on the tides. And that is because, as I said in the beginning, the moon is not the only thing causing tides on Earth. We also have to think about the sun. So the sun also creates tidal bulges on both sides of the Earth that will align with the sun. So they're about half the size as the moon tidal bulges. So the lunar bulges are going to be much larger because the moon has a larger effect. The sun has a smaller effect because it's so far away. But sometimes they line up, so they add together. Sometimes they're offset, so they sort of balance each other out. So this figure shows, here we have what we call spring tides, and that is when the moon is in alignment with the sun. So we have the lunar tide in light blue and the solar tide in darker blue adding together, so the bulge is very strong. So here we're going to have the highest high tides of the month when our sun is in alignment with the moon, which means either at the new moon phase or the full moon phase of the moon cycle. So when we have the sun and the moon in alignment, we're adding the two bulges together, creating our highest high tides. Then when our moon and our sun are offset, so either the quarter moon, so the first quarter moon or the third quarter moon, when we see just the half moon in the sky, this is when we have our solar bulge, the smaller one, in alignment with the sun. We have our lunar bulge in alignment with the moon, but they offset each other. So here we're going to have smaller tides, larger tides from the moon, but they are not going to be as drastically different as when we have our spring tides. So this is called the neap tide. So when you're in the highest tide of the day, it's only looking at the lunar bulge. And then when you're out of the lunar bulge, you're actually in the solar tide bulge. So even when you would be in low tide of the lunar effect, you're actually in high tide of the solar effect. So in neap tide, the difference between the high tide and the low tide is dampened. So if I go back to this figure, you can see that sometimes there's a very large difference between high and low tide. Then at other times in the month, it's much less. So you see there's not as much of an effect. It's not as much of a change from high tide to low tide. And that's to do with whether or not you are situated in spring tides, where everything's in alignment, or neap tides, where things are offset. So if the moon was here at number 4, here's the Earth, here's the sun. If the moon was located here at number 4, what would we see in the sky? Take a second to try and guess. Think about what the moon would look like to us. If we were sitting on Earth looking up at the moon, what would it look like? So in this situation, if the moon was here, it would be fully illuminated by the sun. So the sun would be fully shining on the part of the moon that we see on Earth. So we would see that reflection, we would see a full moon. So a full moon or a new moon is when we have spring tides, when the difference is the largest. So this one, I just gave you the answer, but hey, that's all right. At what positions would the moon be experiencing spring tides? So spring tides is going to be when the sun and the moon are in alignment. So this would be 2 and 4. So B would be the answer here. So 2 and 4. Neap tides would be when the moon is in either position 1 or 3 in this diagram. So on this graph, at what positions, 1, 2, 3, or 4, or which combination of those positions, is this location experiencing spring tide? So where are we seeing evidence of spring tides? So what you should be noticing, as I pointed out earlier, this is the same graph from a couple slides ago. At positions 2 and 4, it looks like there's a very big difference between high tide and low tide in terms of tidal height. Whereas at 1 and 3, the change is not as severe. So if we're thinking about spring tides, that is when the moon and the sun are in alignment. We have really extreme tidal changes. So we would be looking at position 2 and position 4. So in this month of September, around the 8th and then around the 25th, they were experiencing spring tides. So now we know how to explain the daily pattern in tides and the monthly pattern in tides. However, there's another component to think about. Tides are very confusing. So the next thing to think about is the fact that sometimes we have 2 high tides in one day, but they're not the same height. Sometimes they are, sometimes they're quite different. So this is data from Newport Beach. So you'll notice that the high tides here at the start of this month are actually pretty different. Whereas here, the high tides are much more similar. And then again, the high tides are really different from each other. And then here they get more similar. So what's that about? That has to do with our complicating factors. So the first being declination of the moon. So declination of the moon is the fact that the moon does not orbit right above our equator. it actually varies. So as you can see in this GIF here on the right, the moon's location relative to our equator actually varies from about 29 degrees north to 29 degrees south, and it varies a couple times per year, actually many times per year. So the moon's orientation will actually change, which means the orientation of the tidal bulge is going to change. So as you can see in this GIF, as the moon changes, that lunar tidal bulge is going to stay in alignment with the moon. So the peak of that bulge actually moves from further north down towards the equator. So what this means is that if you are standing, say in this example, you're at 28 degrees north latitude, and here in this figure, you are sort of right in the peak of that bulge. So you are in the highest high tide. And then 6 hours later, the Earth rotates. So the Earth rotates, so you are actually on the back of the Earth. So in this, we wouldn't be able to see you because you rotated sort of into the screen, behind the picture. As the Earth spins, you rotate behind the picture, but you're no longer in that high tide bulge. And then, as you rotate 6 hours later, you come back. So now we can see you. You're on the side of our Earth here. You're technically in the high tide area, but now you're in a very lower version of the high tide. So you'll notice that this high tide is very, very different than when you were here in the very, very peak. That's because the tidal bulge is offset. The tidal bulge is not in alignment with our equator in this diagram. Then, of course, 6 hours later, you're going to rotate again over to the front of the Earth out of the tide. So here I have an explanation. Here you're in a very, very high tide. You're in the center of the bulge. Whereas here you're going to be in a lower high tide. So you're sort of in that bulge, but you're right on the outskirts. You're offset from the center. And then here would be the graph of tides based on this diagram as you were standing, let's say 28 degrees north, like this figure, and then if you were on the equator, and then if you were 28 degrees south. So 28 degrees south, at this time, if you were actually at 28 degrees south, you would be in that peak high tide. So that's why you see here 28 degrees south, you're in that peak high tide. So let's see if that made sense to you guys. This is data for Newport Beach. So when, based on this graph, was the declination of the moon close to 0 degrees, meaning the equator? Meaning that the declination of the moon, so the direction of the moon, was actually right here at the equator. So the bulges were aligned with the equator. So take a second to think about what the high tides would look like if the moon was aligned right at the equator. So, if the moon was at the equator, that means our tidal bulges would be aligned at the equator, which means if you're standing in California, you're going to rotate in and out, actually, of the same part of the bulge. You would be rotating in alignment with the bulge. So you would expect the declination of the moon to be at 0 around this period, where the high tides are very, very similar. So where the high tides are the same, because if the bulge is evenly spaced right around the equator, it's not offset from the way that the Earth is rotating. So the Earth rotates, the equator is right in the middle. So if you are rotating in California, the declination of the moon is at 0. That means you're going to rotate into the same height of bulge throughout the day. So for example, here we would expect the declination to be much different than 0. Here it's much different than 0, because here you'd be in the very high tide, here you'd be in the not so high tide, whereas this could have been an answer as well if I gave that as a suggestion or as a possible answer, where your high tides are almost exactly the same throughout the day. That is when you know that your declination is at 0. So the next factor to think about are our orbits. So orbits are not circular, they're actually elliptical, just slightly, very, very slightly, but enough that it does make a bit of a difference. So this actually changes the gravitational forces over the year, over the month and over the year. So when the Earth is, when the moon is closer to the Earth versus when it is further from the Earth, and then the same thing as when the sun, the Earth is closer to the sun versus further to the sun. So when the objects are closer together is when you're going to have more of that gravitational pull, meaning it'll be a stronger tidal influence. The next complicating factor is thinking about the depth of our oceans. So tides are essentially really gigantic, stretched out waves, and they travel at different speeds depending on the depth of the water. So the bulges really aren't totally stationary. As Earth rotates, they get almost broken up because of the difference in the depth in our ocean. So the depth in our ocean, when it gets more shallow, will add friction to that wave of our tides. So the depth of our ocean can have some big impacts on tidal effects, especially near coastlines. And then the other thing to think about, they kind of go hand in hand, is the fact that we have continents. So our continents get in the way. So the shape of the seafloor, yes, just like the slide before, is going to cause some changes in the tidal effects, but also the water ends at some point. We do have continents. So those continents can jut out, they can stick out, for example, they can have funny shapes, which will all have an influence on the way that the tide interacts with the coast and, for example, with the people that live on the coast. So that is, that's all for tides. It was a lot. I know I threw a lot at you just in the beginning of the part of the lecture. But we will look at more tidal data with your groups on Tuesday, and I think it'll be pretty fun. So the main components of our tides are the daily high and low tides caused by the fact that the Earth is rotating in and out of that bulge, and then the monthly cycle of spring and neap tides. So when the moon and the sun are in alignment, we have our spring tides, those really extreme tides. When they're out of alignment, we have neap tides, where the difference between high tide and low tide is not so large. And then we have our complicating factors. The most obvious and easy to point out in the data is going to be that declination of the moon. So the angle. So if the declination of the moon was higher, we would have these lunar bulges being offset. So if you were rotating in the northern hemisphere, you'd be in a very high tide, and then also in a very low high tide, because that bulge would be offset sort of diagonally across what we think of as the orientation of the moon, of the sun. Oh my gosh, of the Earth, excuse me. So for the next part of our lecture, we're going to get into waves, one of my favorite parts of this class. So you don't have to know what all this diagram is saying yet, but you will. So for this part of lecture, we're going to be looking at some appropriate terminology to talk about waves. Then we'll look at wave speeds, wave steepness, and why waves break. And then wave size and different conditions that cause certain types of waves. And then we're going to look at shorelines and how shorelines affect the types of breaking waves that we have. and then we'll look at refraction. So quickly looking at wave refraction, how that affects our coastlines, which will nicely tie into the third part of this lecture, which is all about coastlines. So there's a couple different types of waves. The main four that we will talk about, they're all caused by some sort of release of energy, but the different waves are different releases of energy. So ocean waves, the waves that you think of when you're at the beach, you can maybe see some little white caps on the top on a windy day. That's because ocean waves are produced by air moving across the surface of the ocean. So air, wind blowing across the surface of the ocean, there's some friction there, it's going to create waves looking something like this, or something like this. That's also just called surface waves. Internal waves, so internal waves would be not at the surface, but internal of the water column, and this is waves that are caused by difference in densities. So water interacting with other water of different density caused by either tide or turbidity or winds. So internal waves can be produced actually in the water column because water's interacting. Different water masses are interacting. So in this example, we have low density water on top, high density water on the bottom. As that sort of settles, we will have some internal waves there. Tsunamis we talked about when we talked about plate tectonics. Tsunamis are caused by vertical motion of the seafloor. So some sort of tectonic activity that causes vertical motion of the seafloor. So for example, subduction is where you might find tsunamis. Swell. So swell, if there's any surfers in the class, you might be a little familiar. Swell is a very long-term wave. So waves in the water caused by long-term wind. So wind often from a weather system that is pushing on water for multiple days. So it's something very long-term, pushing the water in a certain direction. That is going to create larger waves that are less frequent. So the wave period is actually going to be larger. So the time in between waves is going to be longer. So those swell waves, if you like big waves for surfing, you're going to want to surf the swell waves. They're larger, but they're usually more, they're less frequent and generally caused by a weather system. And it's usually a distant weather system. So a distant weather system that's blowing on the ocean for a week might send some swell waves across the ocean. So waves, they're really interesting. Waves actually move in a circular pattern. So it's a circular motion. So really the idea is that it's the energy moving, not the water. But really it looks like the movement is in the trough and the crest of the wave. We will have motion actually slower in the trough of the wave, which is the bottom. Motion will be faster at the crest of the wave. So what we call this is wave drift. So there is slight motion in the water, and it is wave drift. So for example, if you had a rubber ducky on top of your wave, you would notice that as the waves move, the duck is actually moving in this circular motion. So as the wave moves underneath the duck is lifted up, and then as the wave moves past, the duck is put back down. So I have a video that I think better explains how waves move. So you'll notice that circular pattern there. as the wave moves through. The ball floating on the wave is actually moving in a circular pattern. So I said a couple of these terms earlier, but just to clarify terminology when we talk about waves, the crest is the peak of the wave. The trough is going to be the low part of the wave. And then the wave height is the difference between the crest and the trough. So that whole height of the wave is the distance, the height difference between the trough and the crest. And then the wavelength is the difference between two crests, or two troughs. It should be about the same. So the wavelength is the distance between two crests. So how much distance between two peaks of the waves. The wave period is essentially how fast are the waves moving. So how frequently do the crests pass by a certain spot. So when do waves break? So if you've been to the beach around here, especially lately, you might have seen some pretty big waves. Waves break due to what we call wave steepness. So wave steepness is how steep is that wave on the shore. So the calculation is just the wave height divided by the wavelength. So the wave height, this distance from trough to crest, this vertical height, divided by the distance between the two crests. And waves generally break when the steepness is 1/7 or more, meaning when the wave height is about 1/7 of the distance between the two. So you can actually calculate when exactly the wave would break based on the wavelength between them, or based on the wave height. Let's try it. So this picture here, this wave is about 6 meters high. Yikes. It is just about to break. So what do you think the wavelength would be here? How much distance does he have before the next wave comes? If this wave is 6 meters high, what would the wavelength be? So what you would do here is the wave is breaking, so you know the steepness but must be about 1/7. So you plug 1/7 in for wave steepness, you plug 6 meters in for wave height. What you end up with is 42 meters. So the wavelength, the distance between this wave and the next one is going to be 42 meters. Maybe he'll have time to get out of the way. So waves travel at different speeds depending on if we're looking or thinking about deep water versus shallow water. So in deep water, the waves don't interact with the ocean floor. So the waves, it's not going to be just at the surface. The influence of the wave actually will reach down a little into the water column, but not that much. So the water movement below about 1/2 of a wavelength. So this, remember, is the wavelength. So below about 1/2 of a wavelength, so if you take this distance in wavelength and put it vertically, below about 1/2 of what this wavelength is, the water is not feeling an effect of the waves. So below there, you're super safe from the waves. The equation for the speed of the waves is just has to do directly with the wavelength and a constant there. So the wavelength below that 1/2 of the wave, you really don't feel the influence if you're in that deep, deep water. So you really don't interact with the waves at all. However, If you're in shallow water, you most certainly are interacting with the waves. So the waves interact quite a bit with the ocean floor if you are in shallow water. So if the floor of the ocean, for example, if the depth of the ocean is less than half of a wavelength, that means that your wave is going to interact all the way down with the whole water column, all the way down to the bottom of the floor. So your speed will actually change. Your equation of your speed will actually change, and it has to do with water depth. So for shallow water waves, this equation here, if finish this sentence, the shallower the water, the blank, the wave travels. Take a second to think about that. So what we're saying here is if we make the water depth smaller, shallower, if we make this number smaller, what's going to happen to the speed? The speed is also going to get smaller. So the shallower the water, the slower the wave travels. So the more shallow your water is, the more that shallow water is actually going to slow down the wave. So when we think about ocean waves, there's a development that occurs. So they don't start as massive waves in the middle of the ocean. Something starts. So wind is generally what creates the start of an ocean wave. So wind is going to create pressure and stress, also friction across the surface of the ocean. So it's going to slightly deform the surface of the ocean. So these are like ripples. And then once this slightly deformed surface interacts more with the ocean surface, the waves will actually start to grow in height. So once this deformed surface is here, the wind is now going to start affecting the deformed surface, increasing how much it is deformed. So the wind will just continue increasing the size of the wave. So the waves are going to get bigger. The waves are going to grow in height. They're also going to get more spread out. So the wavelength will increase, and generally the speed will also increase. Once the wave speed actually matches the speed of the wind, the wave's going to stop growing. So once the speed of the wave catches up to the speed of the wind, it's going to stop growing because the wind isn't pushing it any longer. They're now the same speed. So that is when the wave also would break, because the wind is no longer pushing the wave. The wave has caught up to the wind, so the wave is going to break. It's going to crumble, fall apart. So I have some videos about how big can waves get. So now I'm not talking about crashing waves on the beach. Right now we're looking at waves sort of in the middle of the ocean. How big can waves out to sea actually get? Actually, I didn't play this with music before. I like these tunes. Here's a very, very, very large boat experiencing some very, very, very large waves. Oh, the music is very funny for this horribly scary video. So you can see this massive tanker boat is just getting thrown around in these huge waves. If you're ever in this situation, or on a much smaller scale, maybe on a kayak, on teeny tiny little waves, you want to put the nose of your boat, or your kayak, into the wave, pointing directly in. there's less of a chance that you'll be tipped over. You'll notice that they are sort of steering directly into the wave. Okay, let's look at the next one. Hello. Okay, technical difficulties, that's all right. I'm glad you got to see one. It was another example of really, really big waves. So the actual size of ocean waves are controlled by 3 different things. The speed of the wind, the duration of that wind blowing, so how long has the wind been blowing in that direction. So the wind speed, if you have really high speed blowing in one direction for a very long time, you're going to create some really big waves. The other component is called fetch. So that is the distance that the wind blows in that direction. So the distance that the wind is blowing in that direction. So if you have high wind speeds that are blowing over a very large area in the same direction for a very long time, that is when you are going to have the largest ocean waves. A combination of high speed, high duration of time, and then high fetch, so a large distance covered. So there's another type of wave called rogue waves. Actually, for a while, they were thought to be a myth, not real. But new data has actually shown that rogue waves do exist. For example, here is the wave height graph, a wave height graph, and then you'll notice this massive spike. That would be considered a rogue wave, which, yes, I have a video. Let's see if this one will work today. Oh no. It's here. It's a clip from Deadliest Catch, if you guys watch that show.
180 miles northeast of Dutch Harbor, the Aleutian Ballad is jogging through 40-foot seas and 60-mile-per-hour winds. Captain Jerry Tilley is at the helm, but fishing in this weather is impossible, so the crew has sought shelter below deck.
So they're already in some pretty big waves.
Captain Jerry is deeply focused on the large swells ahead, when suddenly... a massive rogue wave the size of a 5-story building has sideswiped the boat. Rogue waves up to 100 feet high often appear without warning in mid-ocean. The 60-foot wall of water which smashed into the 100-foot fishing boat turned it completely on its side, causing the engines to shut down because of a sudden drop in oil pressure.
So not great if you're out and you get hit by a rogue wave. That's the Deadliest Catch show. I think it's still on Netflix. If you guys want to go watch the whole episode, you're more than welcome to. Rogue waves are really interesting, and I think it's pretty funny that for a while they were considered to be a myth because there was no proof of it. But now we have the data to show it, and of course now we have also the Discovery Channel footage like I just showed you. So rogue waves are caused by wave interference. So there's a couple different types of wave interference, and this is where different waves combine together. So a rogue wave would be caused by something like constructive interference, which is where two waves that are actually in phase with each other, so they're in the same position, they line up, they add together, creating gigantic waves. So waves in phase that get combined or interfere with each other. They interfere, but they're within phase with each other. They're going to create very, very big waves. Destructive interference is where you have waves that are out of phase. So they interfere with each other, they're out of phase, but actually they balance each other out, so you end up with nothing. You end up with no wave. It's destructive. It destroys the waves. Mixed interference is where you have something that is not necessarily in phase and not specifically out of phase. So you end up with wonky looking waves. So you have some destructive, some constructive, some destructive, depending on how the waves and the different pieces of the wave actually interfere with each other. So the rogue wave would be considered constructive interference for the most part. So waves are not simple. There's not just one wave direction. So that's because the wind is not always blowing in the same direction all the time. Sometimes waves will actually come together and it will create really complex patterns. So you'll see this wave pattern here because we have 3 different swells coming in from caused by 3 different wind directions. So where these meet, you actually end up with a really sort of messy looking pattern of waves. So the wave interference can create something very unusual looking, a really, really complex combination of different waves. So another important factor when we're thinking about waves is the seafloor shape. So the shape of the seafloor is going to change the way that the waves break along the coast. So for example, these are pictures of different types of breaking waves. And this here on the left, it has the least steep seafloor. And then as we move through the photos, the seafloor is getting steeper and steeper. So depending on the steepness of your ocean floor, it's going to change the way that your waves break. Waves are also subject to both refraction and reflection. So refraction is when the waves bend. So waves will approach a shoreline, and if the shoreline isn't perfectly straight, or if they aren't coming at a perfect parallel angle to the shoreline, so approaching the shoreline itself at an angle, the waves will actually bend to try and align to be parallel to the shore. So this bending and refraction, so refraction is bending of a wave. It's similar with light, so light can be refracted as well. Waves are refracted along either unusually shaped shorelines or when they approach the coast at an angle. So the wave will bend to fit the coastline. Also, this is going to slow the wave down. So refraction always bends and then slows the wave. So if we look at a straight shoreline, so here is our shoreline. It's straight, but our waves are coming in at an angle. This is actually going to cause movement of the sand. So the sand on the beach is actually going to be pushed along the shoreline. So you're going to have movement of your sand. So this wave is actually going to help deform the way that this beach looks. We also can have very irregular shorelines, so not a straight shoreline. If you had to guess, based on this figure and the arrows showing wave refraction, where do you think the most erosion would occur due to these ocean waves? So the most erosion is going to occur where we have the most concentrated wave power, which would be at B. So as we approach, this would be called the headland of this coastline. we see that the most wave power is actually going to be refracted towards this headland, towards this little peninsula sticking out. You'll also notice in this diagram that this shows that this peninsula is a cliffside, showing that there has been quite a bit of erosion, so eroding along those cliffs. A and C would actually have very, very, very minimal erosion. These would probably actually be depositional environments, so where there would be deposition of sand. So that's why there are sandy beaches here, because the wave power is so focused on B, and the waves are actually refracting, which means they're bending away and slowing down. Here we would actually have an accumulation of sand, whereas here we would have a good amount of erosion. So here's the summary of what I just said. At the headland, where the little lighthouse is, that's where the waves are converging, and we have the energy being focused in that location. And then we also can get wave reflection. So reflection is where the wave actually is reflected or bounces off of an obstacle. So this is Newport, for example, Newport Beach. If you've heard of the wedge down by Newport Harbor, so this is the very end of the peninsula, and over here is Corona del Mar. The waves actually are reflected off of the jetty that keeps the entrance to the harbor open, which what that does is can create absolutely massive waves here at what we call the wedge, the surf spot, because the waves will interfere. So this can become interference, like we talked about, where the waves actually add together, creating even larger waves. So this weekend, I don't know if you guys are aware, but there was an absolutely huge swell in Newport Beach, combined with some really high tides. There was actually quite a bit of flooding on the peninsula, but there were some very, very big waves. So I wanted to show you some pictures. This was just from 4th of July weekend. Excuse me, not pictures, but video.
Oh, hit this, Craig.
Excuse the commentary. I didn't make this video.
Yeah, Craig! What?
Oof. That's a lot of water moving. So it's a really long video. If you guys want to watch the whole thing, it's just on YouTube. There were some huge waves this past weekend. It was very, very cool. So how big can waves get along our coastline? Here is a picture of one of the largest waves in the world, which is called Jaws in Hawaii. So you can see, compared to this person, this is a professional surfer. I got this off of Google. You can see how much larger this wave is than this guy. Yikes. So for the next part of the last part of our lecture, we're just going to talk about coastlines in a little more detail. So now that we've learned about waves, let's think about what those waves do to our actual coastline. So we're going to look at the different factors that control coastlines and what coastlines look like. And then we'll look at sediment transport as well as deposition. We've talked about that a little bit. Look at evolution of coastlines, and then at the end, look at hazards that affect the people that live on coastlines and how these things might change in the future, and talk a little about some ways to protect our coastlines. So coastlines, it really starts with the geology of the coastline. So what is the coastline made of? That is going to influence how that coastline changes in time. So it's all about plate tectonics. So are we at an active margin? Is it a passive margin? Has there been uplift or subsidence? So has the land lifted up or has it sunk down? And then also, what is the coastline, so the continent, what is it made of? Is it very, very resistant, very hard rock? Is it very soft rock? So how quickly is it going to erode? Is there going to be deposition of sediment? What type of sediment? So you can see in something like this, where we have these beautiful coves, a little bit like what we have in Laguna. If you think of this, if you're a geologist and you're looking at this picture, what you're thinking is that, oh, right here, this is very hard rock. This is very soft rock. Here we have hard rock again, and here there's very soft rock. Because what happened is the waves along this coastline were able to very easily erode the soft rock, whereas the hard rock resisted the erosion. Very easily erode the soft rock, the hard rock resisted. So that's where you end up with these coves here. So the shape of the coastline really depends on the geology of what's there, and then how the water interacts with that geology. So for example, here we have 4 beautiful beaches that I would love to go to any of them, but you'll notice that here we have some green sand. Here there's some sand-colored sand. Here we have black sand. Here we have white sand. What's going to cause the difference in these colors? Be what is the sand made of? What material is there that has been eroded down to sand-sized particles and then washed up on this beach? So this is probably made mostly of shells. This is probably made of volcanic rock, crushed up rock. This is more natural sand, just mostly quartz. This might have some other minerals that are causing it to be that green color. So depending on what's there to be eroded down to a sand particle and then deposited is going to determine what color your sand is and what your sand looks like. So sediment really is going to have a big effect on your beaches, for example, like what we just saw. Sediment is often provided by either a nearby river. So this is on the East Coast here. So this is a big river in New England, the Connecticut River. It's going to carry a lot of sediment down that river, which will then be deposited into the ocean. So this sediment can now be mixed and eventually washed on shore. Or erosion by waves. So waves can erode at the rock, at the cliff, creating sand-sized particles, sediment-sized particles that will then be transported along the coastline. So it's our ocean currents that transport sediment. So the currents in the ocean are what is going to carry sediment from place to place. Tides will influence where that sediment can either be eroded or deposited. So the tide is going to determine how high up the water reaches, which means the tide determines how much of the shoreline can be eroded and also how much of the shoreline can be deposited on, because you're going to have erosion and deposition of sediment due to the water nearby. So the water carrying that sediment has to reach those locations. So that is controlled by tides. And then waves really are the main way that rock is eroded. So waves are what is going to chip slowly or sometimes quickly at different materials, breaking them down, and then moving the sediment into other ocean currents. So here I have a question for you. This one's not on your lecture quiz, I don't think, but where would you go swimming? Where, if you were sitting on this beach and you wanted to go out into the water, where would you walk to? Letter A, letter B, or letter C? I'm going to give you the answer because there's a very clear wrong answer, and the wrong answer is B. Do not walk towards B. It looks nice. It looks calm. No, do not go there. That is a very dangerous rip current. I do not want you in a rip current. After taking UCI's ESS 3 oceanography, you have to know not to swim in a rip current. They're very, very dangerous. They're generally very narrow, very strong currents that are moving directly out away from shore. So they sort of cut through the lines of the breaking waves. So here you see that this wave, for example, is sort of broken up by this area of B. That's because it's a rip current. The water is actually flowing out, and it will carry you right out. So avoid this. Do not swim there. No, B is wrong. So the signs of a rip current, I have to teach you a little bit. Sometimes there is a change in color. So there can be, because you have different flow direction, different currents, you can have a change in color. Like we saw in that picture, there's often a gap in your breaking wave, so you can see it as a gap in the wave. Sometimes they have a choppy surface that extends further than the rest of the choppy surface. And if you see anything floating, it's going to be moving fairly quickly, directly outward. So it would look something like this. So this would be the rip current. It's cutting right through this line of waves. You can see it looks very different. You can almost see this perpendicular line right out from the shoreline. So if you are caught in a rip current at any time, it's okay. You can get out, but you just have to know, oh, I'm in a rip current. I can't panic. I have to swim a little bit. So the best thing to do, your first instinct is going to be to swim back to shore. But if you are in a rip current, it's very, very strong, and you might not be able to outswim it. Most likely, you will not be able to. So what you want to do is instead, if you find that you're floating outward very quickly, you don't want to try and swim directly back against that strong current. You actually want to swim out of the rip current. So you want to swim to either side and get out of the rip current, and then you can swim to shore. Once you are not being pulled back anymore, then you can swim to shore. Another thing that you can do is, if you can't get out of the rip current, maybe you're in the middle, maybe it's a little bit wider, you can't actually get out, you should actually let it carry you, because it's not going to go way, way far out. Eventually, the rip current's going to end. You should let it carry you until you can break out, and then maybe you'll be over here. And then again, you don't want to swim directly back to shore. You would want to swim on a diagonal. So they say swim parallel out of your rip current, out of the rip current, or let it carry you and then swim at an angle back to shore. You don't want to try and fight against the rip current. That is the main thing. What I learned growing up was if you're in a rip current, you should wave, shout, and swim parallel. That was the key when I was in the lifeguard school. So always swimming parallel, get out of that current. So that was just my little life lesson for you all. Back to the geology of our landforms. For landforms along a coast, we can have erosional or depositional landforms. So erosional being things that are cut by erosion of our ocean. So cliffs can be cut by the waves. We can have little notches cut underneath by our wave. We can also have sea arches and sea stacks. I have some photos. So here we have a wave cut cliff. So this cliff is cut by the waves. It looks very beautiful. You can see this is actually quite flat, and the waves are just continuing to chip along at these cliffs here. So at our high tide, our wave is going to chip along at all of this cliff. And then we also have other landforms that can form in a sort of pattern. So this is, again, when we're looking at headlands, so sort of that peninsula sticking out. The first thing that will happen due to the increased erosion at this area, because our waves are refracting up to our headland, is the erosion can start to form a crack. And then as erosion continues, that crack is going to grow into a little cave. The cave is going to become larger. With more and more erosion, the waves are actually going to punch through the cave. This would be an arch, a sea arch. So the waves will punch through the cave, and then over time it will be eroded even more until it collapses, and then we'd have a sea stack right here. This sea stack will experience even more erosion, and eventually it will just be a little stump, as they call it. So here is a picture of a sea arch. So this is the cave that's been eroded and punched through. These used to be sea arches. Well, this used to be one big piece of rock. But it was sea arches. The sea arch has already collapsed between these two sections. So this is a sea stack. This is a sea arch. So eventually this will crumble. This will become a sea stack. And this sea stack will continue to be eroded away, getting smaller and smaller. So we also have depositional landforms. So landforms that are caused by deposition of sediment by the ocean or by water. So one of the main ones is deltas. So deltas are formed generally where rivers flow into the ocean. So the rivers are going to be carrying a lot of sediment. They've picked up a lot of sediment as they're flowing down towards the ocean. And then at the coast, the river's going to slow down because it hits the ocean, and it's going to drop all of its sediment. So the sediment actually gets dropped right where the river meets the ocean. So what happens is we have a big accumulation of sediment right at the mouth of the river. A lot of that sediment can then be carried offshore and away and along the coastline. But there will be a big buildup of sediment right at the end of the river, right at the mouth of the river. So this is the Nile, for example. This is the big delta here, all this sediment. And then this is the Mississippi River. So a bit of the Mississippi River. You can see all this very, very shallow area around the river because the river is actually dumping so much sediment there. You're going to have a big buildup of sediment right at the end of the river. And then there's also sediment transport. So it's a little bit depositional. It's not exactly just depositing, but more like moving. So sediment transport being because of wave refraction. So remember we talked about this when the wave is hitting the shoreline at an angle. So we see that bending of the waves as they come in contact with the shore. We actually have sediment transport. So what happens is the wave comes in at an angle, and then as the wave goes out, it's going to carry some sand straight out. And then the next wave is going to come in at an angle, and then that sediment is going to be carried straight back perpendicular to the shoreline. And then the next wave is going to carry sediment in at an angle. As the wave recedes, it's going to move straight back perpendicular to the shoreline. So what happens is over time, you actually move sand down the beach. So this is called longshore drift, caused by what we call a longshore current. So longshore drift is where we have this zigzag pattern because of this refraction along the shoreline, which means that the net movement of our sand is actually going to be all the way down the beach. So some other key terms, especially since we live close by to Newport Beach, where we have almost all of these. A spit is where we have a linear strip of sediment. So a linear strip of sediment that sort of extends away from the land, and it's mostly due to deposition of that longshore drift, like this photo here. Also barrier islands. So this is where a spit actually extends almost all the way across a bay to be a full island. You don't always see these on the coastline. We don't see these on our coast. You can often see them around volcanic islands. But these very shallow and depositionally created locations can be very, very popular to live because you're going to be very close to the ocean, but they're incredibly vulnerable. because they're generally made from deposited sediment. So it's not made on hard solid rock, it's made on unconsolidated sediment, which can be easily influenced by strong storm surge, rogue waves, for example. So very, very vulnerable place to live. So for example, this is a picture of Long Island before and after Hurricane Sandy, which was in 2012. So here we have before and after photos of the before image on the top, and then after the storm moved through, we can see what happened. You'll notice that these arrows are pointing at the same structures. So this yellow arrow is pointing at this house, which it's still here. It lost about half of its square footage, but it's still in the same spot. The road is completely gone. You see the road's totally gone. And then this red arrow is actually pointing to this building here. So you'll see that it was actually picked up and carried in by this water. And this house is much smaller now. You see how much of that sediment has actually been deposited inland. You can see all the roads are covered in sand. All of that sand was carried in by this hurricane, so carried in by the storm surge of this hurricane. And then here is another picture. So this is interesting. The storm surge just went up and over this little spit of land. So this house here, you can see it's actually a lot closer to many of its neighbors. This part was completely washed out. This bridge was completely flooded. All the roads are gone. So this storm, actually, the storm surge went completely up and over this spit of land. Very, very devastating storm. So if we're thinking about depositional shorelines, which direction do you think the longshore drift is moving to create the image that is shown here? So which arrow is correctly signifying the direction of the wind in order to create this shape? Take a second to try and guess. So what you'll think about when trying to answer this question is what was deposited by this wind. So the wind, by this ocean water. So it would have carried the fresh sediment, not the trees in the green, but the sediment, the sand in the white. So what we're looking for is where this longshore drift would have been able to move this sand along this very small stretch of land here. So the right answer would be A, to have this wind blowing, letting the water move this way, curl around, and then deposit the sediment here on this nice beach. B would not be allowing sediment to accumulate. It would be removing sediment from this location. C would be possibly accumulating sediment, but on the inside. So this would be on the inside. So in order to get that sediment there on the outside in white, the wind would have to be, the water would have to be moving along the A arrow. So for the last section of this class, we're going to talk briefly about coastlines and the human influence, the human impacts on coastlines, what we are doing, what we can do. More of this will come in week 5 when we talk about climate change and human impacts on the ocean as a whole. But since we're talking about coastlines, we can look at the different hazards that people will experience at a coastline. So the main hazards that are only getting more hazardous as more people move to the beach and as we develop more near our coastlines are just erosion, coastal erosion, hurricanes, and the storm surge that's associated with hurricanes like we talked about in the last lecture, tsunamis, and sea level rise, so the increase of water there. So many people want to live by the beach. It's usually very expensive to live by the beach, very sought after. However, these things are just getting worse. So what we try and do is control our coastlines. There's a couple different ways of doing that. Different places in the U.S. have different erosion and deposition amounts, depending on the way the coastline is situated. So we can see here, different parts of the U.S. have different erosion and deposition values. So for California, it's a little bit neutral, where in the Pacific Northwest up here, we actually have it's common to have deposition. Here where we have a lot of hurricanes, we definitely have more erosion, so those negative numbers. Along with a lot of the East Coast, there's some of those negative numbers as well. So those coastlines are experiencing more erosion than they are deposition. So what people try to do is we try to stabilize our coastlines. So there's a lot of different things that we can build to try and help keep our coastlines as they are, not let them change the way they naturally would. So for example, longshore drift, we have our zigzag pattern. You notice that the refraction of the waves are coming at this shoreline at an angle. This is going to cause longshore drift. So we are going to eventually be moving sediment from the top of this figure down to the bottom. So one of the things that can be done is build what is called a groin. So if you've ever been to Newport Beach or Huntington, you see those piles of rocks sticking out? That is called a groin, and they're meant to prevent the motion of sand due to longshore drift. So it's meant to catch the sand at one end, and then hopefully eventually it will be pumped back to the other end, back to the other side of the jetty, so that we're keeping sand in Newport and not letting it get washed off the peninsula. So it helps prevent erosion in one area. However, it generally increases erosion somewhere else. So here we're going to have deposition of sand, whereas on the other side of the groin, you're actually going to have more erosion. So it can help keep the sand in generally one place, but you are still moving the sand. You're going to have to pump this sand either over on top or back up to the other groin there. This is an example of a seawall. So this guy on this house has built a seawall on this barrier island to try and reduce the effect of the erosion. However, if the seawall is not strong enough or is not tall enough, a wave, some storm surge, a hurricane might overtake that wall, and then it can be very, very, very dangerous. So in this picture, do you think that the sediment is traveling from the left to the right or from the right to the left? So look at the way that all of those groins are situated, and look at how the sand looks in between. Which direction do you think the longshore drift is moving the sediment? You can also actually see the direction of the waves, so you can see these waves coming in. See how they're at an angle? This is a real picture of Newport Beach. Which direction do you think? So what you want to notice is, if we take this section for example, the shoreline in between these two is not straight. It is not parallel to what we think the shoreline would be. Notice that there's more sand on this side, less sand on this side. That means there's been erosion here, and this groin here has actually stopped the sand from moving, and there's been deposition. So that means that the longshore drift is moving this sediment from the right to the left. So the sediment is being moved even in between each of these groins here, from the right to the left, from the right to the left. So some other ideas besides just the groins or the jetties would be replenishment. So Newport Beach does this every year. I believe Huntington does some beach replenishment as well, but actually putting more sand on your beach. So here they had some groins that weren't exactly working because the shoreline was right up close to these buildings until they replenished the beach, pumping in a significant amount of sand to make the beach larger. So this is very expensive and has to be done pretty constantly and consistently to keep this up. Other ways to think about stabilizing our coastlines, keeping them how they are, would be stopping building. So decreasing the building of construction, decreasing the how much we allow construction along the beach. So you'll see this used to be a beach town. There's still some houses left that were built on stilts. So many of the houses were actually raised up to try and avoid the ocean. That didn't last long, however, and everyone eventually evacuated this location. So the worst comes to worst, abandonment and relocation is what will have to happen if there is no other way to stabilize the coastline. So coastal engineers do lots of work to try and keep our coastlines as they are, especially here where we live, nearby the coast. If you're in Irvine, I mean. But the worst case scenario would be like what these guys had to do, where they just had to leave. So on that very dismal note, that is the end of our lecture for today. Next week, we will begin talking about life in the oceans. So next week will be all about the life in the oceans. So have a good weekend. I will see you Thursday for our Zoom discussion meeting.